Welcome everyone, and welcome to the AluVET Vocational Training and Education for the Aluminium Sector. This training is co-funded by the Erasmus Programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metals series of modules explains the simple theory of metals and of metallurgy to enable students in subsequent modules to understand aluminium, its alloys, aluminium heat treatment, and how aluminium is rolled, extruded, and or welded. This module, we shall be talking about elastic and plastic behavior of metals. This project is funded with the support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. The aim of this module is to explain the elastic and plastic behavior of metals, and to explain what are yield stresses and maximum break-in stresses. This module will enable you to measure and understand yield and tensile strength and elongation of metals, and will help you to quantify yield and tensile strengths and elongation. Well, let's start understanding about stress and tensile strength. If you hang a load, a weight, on a wire, a filament or object, the weight will put the filament or the wire into tension. That is, it will stress it. The weight applies a force into the filament, a stress. Depending on its strength, that filament will stretch and elongate, so will be strained. When you hang a weight on a filament, you actually stretch the filament depending on the strength of the filament and the weight that you hang on. As an illustration, you are sitting in a seat, and your weight that you're exerting on that seat is stressing the seat. It actually imparts a force into that seat that you're sitting on at this very moment. Assuming we keep the filament exactly the same, so same dimension, same strength, and change nothing. Depending on its strength, that filament will stretch, that is, elongate under the hanging weight. The heavier the weight, the greater the stress, so the resultant stretch of the filament. So if we change nothing about the filament and hang a bigger weight on it, we will stretch that filament more. Stress is a measure of strength, the ability of something to withstand a force. And in our example, that is the weight or the load. And we plot the measures of stress on the vertical axis, the y-axis of a graph. So we plot stress on the vertical axis of the graph, the y-axis. Strain is a measure of stretch or elongation, and we plot strain on the horizontal or the x-axis. Thus, we can construct a graph of stress against strain. Stress is vertical, strain is horizontal. As we saw before, hanging a weight on the filament results in loading or stressing the filament, so we'll stretch or elongate it. And we can plot the stress, the weight on the vertical axis, and measure the resultant elongation on the horizontal axis. So in the graph, you can see the weight, the stress that we've applied, and the resultant stress. The blue line represents the elongation of the weight. If we increase the weight, the increased stress will result in the filament stretching or elongating more. The greater the weight, the higher the stress, the greater the resultant strain. We plot the increased stress on the vertical axis and the measure of the resultant elongation on the horizontal axis. When loaded or stretched or stressed metals, when loaded or stressed, aluminium will stretch or elongate. We need to look at the effect on an atomic scale and in terms of the planes of atoms. So when we stress a metal, we have an effect on the planes of atoms. So when we stress aluminium, it will stretch or elongate. Now remember, the clouds of electrons hold the atoms together through the metallic bond. So effectively stressing stretches the planes of atoms, but importantly does not slip the planes. So you can see in the slide, we are stressing the planes of atoms, but they haven't slipped. Low stresses do not slip the planes of atoms. The positions of atoms relative to each other does not change. There is no reshaping or permanent deformation of the metals. So at low stresses, we stress the atoms, but we don't reshape them. So when stressed by a load, the metal atom grains stretch in exactly the same manner as the planes of atoms. Remember, the planes of atoms are held together by the metallic bond. On removal of the load, the metals, aluminium, springs back to its original shape. There is no permanent deformation. The planes of atoms have not slipped. At these low stress levels, loads, the metals behave elastically. They spring back. They spring back just like an elastic band. There is no permanent reshaping or deformation. So at low stress levels, as we apply the load, we stretch the aluminium. When we take the load off, the aluminium springs back elastically. The aluminium, the metals return back to their original shape. On removal of the load, the grains spring back, they behave elastically. There is no change to the shape of the grains. So at low levels of stress, we elongate the grains, but as soon as we take the force off, they spring back and there is no shape change. If we keep increasing the applied weight, that is increasing the stress, so apply a bigger load, there is suddenly a large increase in stretch. That is elongation. The increase in elongation is very marked and very large for such a small increase in stress. So in the graph, you can see we've increased the load. For a small increase in load stress, we've suddenly seen a big jump in elongation. And at this point, the straight line relationship between stress and strain breaks down and the graph curves away. So up to this point, as we applied the load, we had a straight line relationship between stress and elongation. At this point, we've lost it, and now the graph curves away. This is the yield stress or yield point of the metal. Up to this point, the yield point, the yield stress, the metal has behaved elastically. It has been a straight line relationship between stress and strain. Now we've exceeded the yield, it no longer behaves elastically. Beyond this point, the relationship between the applied stress and the measured elongation is no longer linear. It no longer follows a straight line relationship. What's happened? Once the applied stress exceeds the yield stress, the deformation becomes permanent. The planes of atoms have slipped. They have moved past each other. You can see in the diagram, they have slipped. The slip in the planes of atoms results in a shape change of the metals. So we have now slipped the planes of atoms. We've changed the metal shape. Remember, the atoms are still held in their new position by the metallic bond. The planes of atoms have slipped. We've now got permanent deformation. Now, up to the yield stress, the elastic stretch is a straight line relationship between stress and strain. So up to the yield stress, the yield point, as we apply low loads, the stretch is a straight line relationship between stress and strain. And it follows a straight line equation. Stress equals slope times the strain plus a constant. So up to the yield stress, as we apply a load, the relationship between stress and strain is a straight line.